So how do we compute the determinant of a 2 by 2 matrix? The general formula is AD minus BC. So the product of the diagonal minus the product of the off diagonals. So here that would be 4 minus 6, which is negative 2. What is the determinant here? 1 times 4 minus 2 times 3. It's also negative 2. What's the big idea here? It's that the determinant of a matrix is equal to the determinant of its transpose. See, this is the transpose of this matrix. The first row was 1, 2. Now the first column is 1, 2. The second row was 3, 4. Now the second column is 3, 4. These matrices are transposes of one another. They have the same determinant. What's the determinant of this one? Well, that's going to be 2 times 3, which is 6, minus 1 times 4, which is 4. That gives us 2. How did we get this matrix? We swapped the order of the columns. And what we're seeing is that swapping the order of the columns gives us the opposite signed determinant. Okay, just as an example, what if we started with this matrix, 1, 2, 3, 4, and swapped its rows? Then we get 3, 4, 1, 2, and this determinant would be 6 minus 4, which is 2 as well, which is showing you that when you swap the columns or you swap the rows, if you make any one of those swaps, the determinant gets multiplied by negative 1. Now, if you do both of those swaps, so if I swap the rows to get here, and then swap the columns again to get 4, 2, 3, 1, the determinant is back to being 4 minus 6, which is negative 2. So if you make multiple swaps, the determinant gets multiplied by negative 1 multiple times. So that's a little bit of 2 by 2 determinant math for you. Now the next activity asks for the determinant of this 3 by 3 matrix. And here, this is really just a question of applying a formula. So let's apply it. The matrix is 4, 2, 0, 3, 1, 1, and negative 6, 2, 5. So the formula is in the notes, but here's how I like to visualize it. The determinant of a 3 by 3 matrix comes from doing the top left element times the determinant of this 2 by 2 matrix down here. So I'll write this as the determinant of A is equal to 4 times, I'm going to use this symbol for the determinant, 1, 1, 2, 5. It kind of looks like the absolute value of a matrix. That's its determinant. Minus, now we're going to go up here. We're going to go do minus this element, so minus 2 times the determinant of everything you get when you remove this row and this column. So that's going to be the determinant of everything without the first row and without the second column. So it's going to be the determinant of this 2 by 2 matrix you get when you take those two sort of subvectors in here. So 3, 1, negative 6, and 5. That's the same thing we did to get this first submatrix. It was 4 times the determinant of everything without 4's row and without 4's column. So I covered up that stuff, and that's where I got the 1, 1, 2, 5 from. Now it's minus 2, so the signs will alternate, times the determinant of everything you get when you remove this row and this column. And that's where the 3, 1, negative 6, 5 came from. The signs alternate, so now I'm going to have a plus 0 times the determinant when you remove the row and column 0 is in. So I have 3, 1, minus 6, and 2. And if I had another thing here, so if this matrix was 4 by 4, it would be minus whatever that number is times the determinant of whatever I get when I delete the row and column that number was in. So now all I need to do is find 3 determinants of 2 by 2 matrices, and I can stitch those together to get my 3 by 3 determinant. One of them is easy. I could compute this determinant if I wanted to, but I don't really need to because it's going to be multiplied by 0. So that term goes away. What's left here? I have 4 times this determinant. What's that going to be? 5 minus 2, which is 3. And then here I'm going to have 15 minus negative 6. So what does this stitch together to? So I have 4 times 3 minus 2 times 21, which looks like 12 minus 42, which looks like negative 30. So that's the determinant of this 3 by 3 matrix.